Okay, so thank you all very much for coming this morning. Today we are happy Michael Gekhtman from University of Notre Dame, and he will tell us about the generalized cluster structures related to the Drinfeld double of the GLM. Please.
All right. Thank you for the invitation, and apologies to those who may have seen the version of this talk before. This is a joint work with Misha Shapiro, who can correct me if I'm making any mistakes today, and Alec Vainshtein. And well, you can find this information in these three papers that I listed here. Since I don't know if I should expect everyone in this particular seminar to be well-versed in cluster algebras, I thought that I'll probably start with just general setup of what we're trying to do, and then well, hopefully we'll get to the actual topic of the talk eventually, right? What we're interested in is uncovering cluster structures on Poisson varieties. So I'll go over the detailed definition later, but the general strategy is as follows. So we have some Poisson variety, which well, usually admits a toric action, even though I will not focus on this today. And what we want to do is construct a family of really nice coordinate systems on this Poisson variety, which are subject to several properties. First of all, we want in any of the coordinate charts, we want every coordinate function to be a regular function on our variety, and we want it to be homogeneous with respect to the toric action. So in our examples later, you'll see something like, well, you have a space of matrices, and the diagonal matrices are acting on both sides, and you want your coordinates to be polynomials homogeneous with respect to this action. Then we also want, and this is a very strong requirement, this coordinate chart to be what we call compatible with the Poisson bracket in the following sense. So this is a bad term for people well familiar with Poisson geometry. So it's not compatible in the sense of a Poisson pencil, but just in this sense that I indicate here, that it is really simple bracket, right? It's quadratic, so-called diagonal quadratic or log canonical. So bracket of every two functions is just their product times some constant. There is no summation here. Also, we want any two of these charts to be connected via Laurent polynomial transformation. So it means that it is Laurent polynomial transformation, and its inverse also is Laurent polynomial. And finally, we want any regular function on our variety to be recoverable as a Laurent polynomial in terms of every of these coordinate charts, right? So this is what we're looking for. And later on, I'll restate all of that as saying that we have a cluster structure in our Poisson variety. So maybe I should look at the simplest possible example of where this is happening. And this is just GL2 with a standard Poisson-Lie bracket, which I just listed here. So it's already almost log canonical. You see, well, among the six Poisson brackets between matrix entries, almost all of them has this log canonical property, except for this one. And we have a Casimir, which is a determinant. So what is this nice coordinate chart? In this case, they're very simple. You can pick either A, B, C, and the determinant, or D, B, C, and the determinant. And there is an easy transformation between these two charts, well, which is essentially a formula for the determinant, but I will write it in subtraction-free form. And so here you can see it. And to remember this formula, you can record this formula as a quiver, right? So this quiver, this directed graph, just tells me that if I want to transform A, I have to multiply all the variables that points to A plus add the product of all the variables that to which A points, and then divide by A, and this will give me a new coordinate. And this is a typical example of a cluster transformation and of a quiver mutation. All right, so we'll talk about this later. But so this is a complete structure because every matrix entry can be restored just as a cluster word. All right, so that's an example of a cluster structure on a Poisson variety. And now let me go over this in more detail. So we have the following ingredients. On the Poisson side, as I said, we have this variety equipped with a toric action. And well, what we're looking for to construct this family of coordinate charts, we're looking for at least one of them. And so we will denote it by X. And there are variables that we will transform eventually. There are functions that we will transform. And these blue functions, frozen functions, we will never transform. Since we have this nice Poisson structure, I can record it as a single matrix omega. And I also assume that all of these variables are homogeneous with respect to my toric action. And so what I do, my transformation of coordinate system is just throwing away one of these coordinate functions and adding another one in such a way that it will still preserve this log canonicity property. So this property is still satisfied, maybe with different constants. And in such a way that these new variables are also homogeneous under the action, right? So this is on the Poisson side. And on cluster algebra side, this coordinate chart gives me what gives rise to what's called an initial seed. So the same function, same coordinates are called initial cluster. And there is also initial quiver, which will determine my cluster transformations. In relation between this quiver and between my Poisson structure here is as follows. So I can start with a quiver, I can record its adjacency matrix, and the property is that the product of this adjacency matrix times my matrix of Poisson parameters is going to be of this very simple form, just lambda times identity and 0. And you may wonder why this adjacency matrix is not square. It's rectangular, and the reason is that I'm going to ignore adjacencies between so I will ignore adjacencies between frozen variables. So we in our quivers there will be no arrows between frozen variables. All right, so that's how I define the quiver. And then given a quiver, I will define the exchange relation exactly as in our example. Old variable times new variable is going to be product over vertices which point to this particular vertex in the quiver, and plus product of vertices to which this particular vertex points, right? So and that's how we define exchange relation. And then the theorem is that if you transform your coordinate system like this, then you will have this log canonical property preserved. But you do need to check a few things. You need to check that your new functions are still regular functions. This is not a given. This has to be verified. This usually follows, well, it happens for some reason. And then we also need to check completeness. And so completeness, as I said, means on the Poisson side that every regular function is Laurent polynomial in terms of every of these coordinate systems. And on the cluster algebra size, which just says that the ring of regular functions is naturally isomorphic to so-called upper cluster algebra, which, well, I don't want to go into this right now, but what it means is simply that you can express, so you can express every coordinate function as a Laurent polynomial in terms of this of any coordinate chart. All right, so that's the definition. All right, so Right, and when we perform this cluster transformation, we also, well, so our Poisson bracket changes and quiver changes accordingly, and this is recorded in so-called quiver mutation, which is probably well familiar to everyone by now, but I just presented an example of what's gonna how this quiver is being transformed, right? So we add shortcuts, and then we remove two loops, and we reverse all the arrows which are adjacent to this particular vertex in our quiver. All right, so let's consider another example of this cluster structure, which we will revisit later. And this follows work of Young and Zelevinsky. So here we consider GLN with this, again, standard Poisson-Lie structure. It's well known now that there are regular Poisson submanifolds in GLN called double Brea cells. And in particular, here I'm going to consider Coxeter double Brea cells, which without reminding definition, in this case, I can just describe as a set of tridiagonal matrices, invertible tridiagonal matrices with non-zero off-diagonal elements. And what you can do is you can define initial seed in a very simple way. First of all the off-diagonal entries will be viewed as frozen variables. We're not going to touch them. So you then define just trailing principal minors of this tridiagonal matrix as the original set of variables. And you can verify that they indeed have this nice log canonical bracket with respect to standard Poisson-Lie structure. And then you can compute the quiver as I indicated on the previous slide. This is not how Young and Zelevinsky, or previously Bernstein, Fomin, and Zelevinsky did it, but you can do it this way. The quiver will have this very simple structure, and if you ignore the frozen variables, this will look precisely as Dinkin quiver A4, which means, according to Fomin-Zelevinsky series, that this is a cluster algebra of finite type. So we only have finitely many cluster variables. And in this case, first of all, cluster transformations will be just instances of classical determinantal identities of Denano-Jacobi, or if you wish, short-Plücher type. And you can describe all cluster variables as just dense principal minors of this tridiagonal matrix. So that's another example. So and therefore will have completeness, because in particular it will include all one by one dense principal minors. So all the entries of X will be restored. So we will see a generalization of this later. All right. So let's consider, well, more complicated example, and this will be a Drinfeld double of GLN. So here I want to, so we're looking at, well, as I said, a GLN cross GLN. Again, we're dealing with a standard Poisson-Lie structure on GLN, and then the double decomposes into a product of a diagonal embedding of GLN equipped with the standard Poisson-Lie structure times the dual Poisson-Lie group. And double itself is as well known as a Poisson-Lie group. And so we can write down a Poisson bracket, which is quadratic in terms of matrix entries of pair of n by n invertible matrices, which will not be a log canonical, of course, but you can find this log canonical coordinate. So let me give you an example for n equals 2. And so what you see here is that, well, you can select this function. So I just listed them all. It's very simple functions which are log canonical, and you can construct the quiver as I indicated before. But then there is a problem. If I want to mutate, then well at vertex say x2, I will, according to my rules, then we will get a nice polynomial function. The same happens here, but in this hexagonal vertex, well, if you do the same, you will not get a regular function. You'll get a rational function. And so we don't want that to happen. We want to stay within the category of regular functions. And there is a remedy. You can make your transformations a little bit more complicated. Namely, instead of allowing in the right-hand side of transformation only binomial expressions, you can allow longer expression. In this case, it will be three-term expression. And so this is how it looks. This is an easy identity to verify. So this was my cluster variable. And it turns out that it can be transformed into new regular function if you use a three-term polynomial in other cluster variables with coefficients which are not just random coefficients, they're actually Casimir's for our Poisson bracket. So, well, determinant of x, determinant of y, and then just the middle term is a coefficient is a characteristic polynomial of the form x plus lambda y. So this is an example, a prototypical example of a generalized cluster transformation, and that's what we want to do. We want to study generalized cluster transformations. So let's move from this double of GL2 to double of GLN. Well, situation clearly is going to be more complicated, but I'll try to describe it, as a cartoon here. So, well, first of all, we need a lot of log canonical functions, and they can be. So this is what we discarded with Alec and Misha. You can select them in the following way. So some of them are just functions that are familiar in a cluster theory of GLN itself. So you have just dense minors of X, one of the end elements in GLN, which are attached to the last row of matrix X, similar dense minors of Y, which are attached to the last column. And then there are this kind of mixed determinants of X and Y. And then these gray functions are very strange looking functions, but they are still polynomial regular function, and all of these functions are log canonical. And we have this special vertex over here, and this is the one that cannot be transformed according to usual cluster rules, but it can be transformed if you use generalized transformation of the following form. So you take the function, we call it phi1 that sits here, and it transforms into a regular function, again, phi1 tilde, according to the following formula. So this obviously, if you expand the determinant, it will be expression of length n+1 rather than 2. So it's a generalized cluster transformation. All right, and one can show that this generalized cluster structure is regular, it is complete, so it has all the nice properties. And in fact, it contains several important clusters in generalized cluster structures. So let me list them. So in this picture, you can find, so you can restrict it sort of on the, so apart from being a generalized cluster structure on the double, you can restrict it to GLN. If you restrict it to GLN, you just considering it on the diagonal, then all this middle rhombus, all these functions will vanish, and this yellow and this blue will be identified, and you will obtain the standard initial cluster for the standard cluster structure on GLN. So it's not generalized. Similarly, you can reduce to the dual Poisson-Lie group, and then, well, this the wings of this picture will fall off, they will disappear, and then you'll have a regular complete generalized structure on GLN star. And you can reduce further to a structure on the conjugacy classes on GLN intersection with just big Brussels B plus B minus, which is of interest to people studying Coulomb branches. And then you can restrict even further just to this upper triangle. And then this will be a generalized cluster structure on the smallest Brussels B plus W0, right? So, so as you can see, in this case, there is only one generalized relation again. And so maybe we want to figure out the nature of such a relation. And the idea is that, well, as I said, all cluster transformations and all the examples, they one way or another are related to classical identities, from Ptolemy identity to Denano-Jacobi to Plücker relation, if you wish, Hirota equation. So they're all of the same nature. And so we want this to see if there is a family of geometric examples in which generalized relations are also of the same nature. And so we found this identity, which we'll call also this main master identity, which, well, it looks much less pleasant than Plücker relation. So let me just briefly describe what's important here and then what's maybe not so important. So we have an n by n matrix, right? And we build from and we fix two vectors. We build from this matrix what's called a cyclic matrix generated by A and vector U. What's important is that it is still polynomial in terms of entries of A. And then we also build this kind of almost cyclic matrices. Again, the polynomial in terms of A. And well, we'll have to, well, consider classical adjoint of one of these matrices. Again, polynomiality is important. And the identity is the following. So you have determinant into, well, of some polynomial function times A minus another polynomial function times identity. And it factors into two regular functions. So one is this initial gamma of U, this determinant of the cyclic matrix, and another one is built also a cyclic matrix by, well, of a more complicated nature. Again, what's important here is that, well, this determinant, this characteristic polynomial into which you plug particular polynomial functions will factor, right? And that is a model for our cluster transformation. Okay, so now that we have a model, maybe I need to go to through the definition actually of what is the initial seed for generalized cluster structure. So this is a generalized cluster structure of geometric type, and this is our modification on previous definition of Misha Shapiro and Leonid Chekhov. And it's not the most, I don't want to present the most general situations. I just want to describe a situation still associated with quivers. What's the difference between this and the standard cluster structure? We have a quiver, and we associate to each quiver now a multiplicity di, which will dictate the length of a generalized cluster transformation, and also a string of coefficients, which has this properties that the first and the last coefficient are 1. Okay, and so now I have to build from this quiver. So there is, as before, a cluster variable attached to every vertex, and I have to build a generalized exchange relation at any vertex. So the left-hand side always looks the same. It's old times new, but the right-hand side now changes. It becomes longer, right? So we have length of this relation is dk plus 1. Corresponding multiplicity plus 1. It involves its coefficients. And then it is a little bit more complicated in terms of monomials that are involved in the relation. So we have the usual ones. So take all non-frozen variables from which to which our fixed k point k points, and take all non-frozen variables to which points to K and consider corresponding products. But then with frozen variables, we do something more complicated, and it's unpleasant looking, but this works, right? This is the only thing that works. So we take the product of frozen variables to reach K points, but instead of raising into powers, well, so we'll have to divide by the corresponding powers by the multiplicity. It is not necessarily integer, so we'll take a floor function here, right? So it's still monomial, it's still integer, monomial with integer exponents. So that's how you build this relation. And then this is how your variable mutates. Coefficient mutation is very simple. It just switches order. And then quiver mutation can also be modified in a nice way. So where in the usual definition of a quiver mutation, I would, if I see a path I, K to J, I would add a shortcut. Here, if degree of my vertex K is dk, I will add dk arrows. And the same thing here. Right, so that's how you change the definition, and one can show that under these definitions, all the properties that we love about cluster algebras remain intact. So you have the Laurent phenomenon and all other properties, compatibility with Poisson brackets, they will remain the same. And this was investigated by many people. But so any properties that you want will be with suitable modification satisfied. All right, so we had an example of generalized cluster structure. Now we have this general definition, and maybe it's good to look for more examples. And so this is what we did, and it turned out that there is a nice source of examples where you use versions of our master identity, and then you can build this generalized cluster structures at some natural objects. And the nice source of examples is so-called periodic staircase matrices. So, what it is shown here. So just imagine that you have infinite, block toplets bidiagonal matrix. So you have blocks A, B of size n by n, and it's just expand in both directions. And we also will say that this matrix has k inner diagonals, which means, so I described it in a picture. So inner diagonals means that, if you view such diagonal as a main diagonal over your infinite matrix, right? You have a choice because it's double infinite. So if it uses is as a main diagonal, then the whole matrix is not reducible, right? So, here's an example where we have precisely two inner diagonals. All right, so this is our object. And when we deal with all examples which are built on GLN, on homogeneous spaces GLN, it's often convenient to define our cluster variables as some trailing or leading principal minors. But here we have a problem because usually you start in a corner and continue from this corner. Here you cannot do that. So to remedy this, what we do is the following trick. So we have this infinite periodic matrix. I'm going to remove first row from each block row, and then the matrix will become eventually reducible. It will have the maximal irreducible component of size roughly equal to the number of inner diagonal times the size of original block. So here's an example. Here I look at 5 periodic four diagonal band matrix, right? It's infinite, but if I will remove the first row from each of these block rows, then my matrix becomes not as pretty, and so you can see that eventually it becomes reducible. So I have this now irreducible, maximal reducible component, which I will call phi. Okay. All right. So how are we going to use it? Now I have well-defined kind of lower right corner, and I'm going to define a family of functions, which again are built as trailing principal minors of this irreducible block phi. So there will be this n capital of them. And I claim that if we define the characteristic polynomial associated with our band initial staircase periodic matrix, just determinant of lambda b plus mu a, so we'll write this, we can record coefficient, then our previous master identity can be restated as follows. So the determinant of this entire block phi, which we will call phi1, times a new function is equal again to this sum I goes from 0 to k, so sum of the number of inner diagonals plus 1 with coefficients which are the coefficients of the characteristic polynomial times powers of some well, first of all, other determinants that we defined, and well, maybe determinant of, well, some of the, well, reduced blocks in our original matrix. So it looks kind of like generalized cluster relations, and in fact we can make it in several examples into a generalized cluster relation. So we will just need to find a natural situation where all the ingredients, this one and this one and this one, belong to this nice log canonical system of coordinates with respect to appropriate Poisson bracket. Okay, so that's what we will try to do. So I'm going to back to our example for the double, and we will construct maybe less strange initial cluster for generalized cluster structure there. So in this case, so A is X, B is Y. So in this case, we just, just consider this infinite matrix with blocks X, Y, and so on. And if I remove the first row of each block row, then I will obtain the following well animal. This phi of lambda, it will be of size n times n minus 1. And I can now use this in order to find initial cluster for generalized cluster structures on the Drinfeld double. Namely, well, first of all, let me list the functions. So what we have is, well, this trailing principal minors of phi of lambda, there will be n times n minus 1 of them. Then you take again dense minors attached to the last row that corresponds to X, dense minors attached to the last column that corresponds to Y. If you compute how many total number functions you have here, you will see that it's still not quite 2n squared, which is the dimension of the double. But remember that we also have coefficients of characteristic polynomial determinant of lambda x plus mu y, and those are Casimirs of the corresponding Poisson bracket. So they will not be present in the quiver, but they will be present in the generalized relation. And so we have this family, and we have this well, nice enough quiver. And the claim is that this family, together with this quiver, defines an initial seed for a regular, complete generalized cluster structure, which is compatible again with the standard Poisson-Lie structure on the Drinfeld double. And the only generalized relation will be corresponding to this place phi1. All right. So it's a different initial seed than the one I described before, so maybe I should make a few remarks. So first of all, for n equals to 4 already and conjectural for any n, we proved that this cluster structure is actually not equivalent to the ones that we discussed before. So, and this is an interesting example. So they're compatible with the same Poisson bracket. They have the same frozen variables, but there is no cluster transformation for n equals to 4 when you can, well, start mutating the initial cluster for one and get into initial cluster for the other. Right. So it's rather surprising result, but we have conjectures that both these generalized clusters can be embedded into a larger cluster structure on a larger variety, and they will become equivalent there. And so this larger variety conjecturally is closely related to the Poisson version of the quantum cluster structures that Gus Schrader and Sasha Shapiro considered when they found quantum Tor embedding for universal enveloping, quantized universal enveloping of GL. All right. So here's another example. So, well, I used periodic band matrices before as an example. So let's consider the case of periodic band matrices. So we have periodicity of length n, and we have k+1 diagonals. So this is well, an important object both in classical spectral theory and also in integrable systems. So or well, like periodic total lattices and their friends. And versions of them live on the space of band periodic matrices, or well, more recently things like generalizations of pentagram map can be realized in such matrices. So we'll perform the same trick. We will remove the first row of each block row. This n, the size of the maximal reducible component, in this case, it's n-1 times k-1. What is the corresponding Poisson structure? So we can consider this set of, well, just linear polynomials in lambda with coefficients a and b. This will of this particular shape. This will form this forms a Poisson submanifold in GLN lambda, right, in loops on GLN with respect to trigonometric R matrix bracket. So this was also recently considered by Isosimov in connections with pentagram maps. So this is our Poisson structure. And again, the claim is that if you consider the families that I just described, all this, so this minors built of the matrix phi that we built from this infinite periodic matrix, and if you view all the entries of outermost diagonals as frozen, then these functions will, together with the quivers that I copied here, will define a regular, complete, generalized cluster structure, which will be compatible with the restrictions of trigonometric R matrix bracket. All right, so maybe this is time to go back to this example of Young and Zelevinsky that we talked previously was finite tridiagonal matrices. So what happens if k is equal to 2? So meaning that we have just tridiagonal periodic matrices. So in this case, this generalized cluster structure is turned out to be of finite type, but not of finite type an-1, as before. This will be of finite type Cn. And the cluster variables in this case will again correspond to distinct dense principal minors of size less than n, but not of the well, so not of the finite matrix, but of the infinite tridiagonal matrix. So it's still, so another nice realization of a generalized cluster structure of type Cn. And there are some other nice things to consider in this situation. So let me use them, consider them, or list them as remark. So it was observed by Anne Gleit's student of Bernard Leclerc that, in the case of representations of UQSL2 hat at roots of unity, the Grothendieck ring of certain tensor subcategory of finite dimensional representations is actually generalized cluster algebra of this type C. Well, in that case, it was CL minus 1. They considered L to be roots of order of Q square in this case. So this very structure, where you ignore the frozen variables, so this just consider just this part, appears in the study of representation of UQSL2 hat at roots of unity. And what we observed, so Glide's conjectures that similar result is true for UQSL3. What we observed with Chris Fraser and Trey Trample is that her conjectured generalized quiver is mutation equivalent to our quiver for band periodic matrices in the case of four diagonal in the 4 diagonal case. This will be the quiver, and so we're trying to extend it to a general case, and there is also connection of our of the structures that I'm describing on band matrices. There is a connection to with Fraser's work on cyclically symmetric loci in Grassmannian. So these structures become what's called quasi-isomorphic. It means that, well, the essential is the same up to multiplication of cluster monomials, cluster variables by monomials in frozen variables. All right, so that's another example. And okay, so I have the next part, which usually, well, which has a subtitle time permitting, and for the first time, time does permit me to talk about it. So maybe I'll try to do this. In all previous examples, we had exactly one generalized relation. And so the question is it possible to find natural situations in which you have several of these generalized relations? So, because our general definition allowed for any number of generalized relations, but it's nice to have examples of that. And so this example will come from our study of exotic cluster structures on GLN. So what is that? So as we so all the previous examples dealt with the standard Poisson-Lie structure on GLN. But there is a Belavin-Drinfeld classification of Poisson-Lie structures, which, well, gives a rich family of such Poisson-Lie structures. And so what we have been doing actually for a long time is describing cluster structures that would be compatible with this non-standard Poisson-Lie structures. And we describe this completely for GLN in the case of so-called aperiodic Belavin-Drinfeld data, which I will explain in a second. But there is a situation when you actually have to consider generalized cluster structures. So let me just remind you what this Belavin-Drinfeld Poisson-Lie structures are built from. What you start with is two subsets of simple positive roots, which are isometric and satisfy certain nilpotency conditions. So here's an example. I have roots, well, this is an example from GL6. So I have roots alpha 1 and alpha 5 that are being mapped into roots alpha 3 and alpha 2 and alpha 4. This is a nilpotent map in a sense that, well, I will eventually, by repeating, applying iterations of this map, I will eventually leave the set gamma 1. So our construction of cluster structure for compatible with corresponding Poisson-Lie bracket is reliant on the following combinatorial objects. So what you see here is two copies of Dinkin-Pure A5, where I just neglected to draw these edges because of actual Dinkin-Pure, because we don't need it. And so you can build from it the following graph. So you have just these arcs, which essentially represent the action of negative W0, where W0 is the longest while element. And also we have these edges that just represent this map gamma 1 to gamma 2. And well, when you draw this graph, you will see that it may or may not have cycles. So this one does have cycles, and this is what we called, so if it doesn't have cycles, we call it aperiodic Belavin-Drinfeld data, and this is not aperiodic. And it turns out that if you want then to construct cluster variables, which will be log canonical with respect to associated Poisson-Lie bracket, what you can do is use this graph in order to build this, again, block bidiagonal matrices made out of pieces of submatrices of an element XY that also XY that lives again in the double. In this case, it's in the double and GL6. So they are built through certain natural procedures. So every X block will contain the lower left corner, every Y block will contain the upper right corner, and they behave naturally with respect to certain subgroups in the double, which are determined again by the Belavin-Drinfeld data. But the thing is that if our graph here is aperiodic, then all such matrices, so there will be several of them, but all of them are going to be finite, and then we can just take again trailing principal minors, and this family we can prove gives a log canonical coordinate system. But whenever you do have cycles, each cycle gives rise to a pair of infinite block periodic staircase matrices. And then the claim is that by applying our procedure to both of them, you will contain, you will obtain the maximal necessary family of log canonical coordinates, and for each of these matrices will have one generalized relation. So this is the first example where you have a generalized cluster structure associated with the Belavin-Drinfeld Poisson bracket. All right, and I think I'll just thank you here and stop.
Thank you. Questions? Yes.
I have a question.
Yeah.
So the cluster algebra or cluster coordinates on double Bria cells, they come from factorization into SL2 triples.
Right. Yeah.
And I'm just wondering, and mutations are also related to this.
Right.
So it's a very simple idea that sort of originated the whole business.
Right.
And I'm just wondering if the generalized cluster coordinates have the same nature.
So this is a very, very good question, and we clearly thought about this, but there are two issues here. So one is, so you can embed, as I mentioned earlier, this generalized cluster relation into larger cluster algebra, and maybe there is a way to, at least for standard, for things associated with standard Poisson brackets, you can make sense of this factorization.
Ah.
But say for this Belavin-Drinfeld business, well, you no longer have this nice Poisson-Lie, simple two-dimensional Poisson-Lie subgroups, and because of that, the proof of the fact that this coordinates that we build actual log canonical, the proof is just horrible, right? So I just couldn't, because in the absence of factorization, so clearly there needs to be a replacement of this factorization. We just don't know yet what it is, but yeah, that would be the goal. And also you want, well, one would want to consider this network realizations of all of that. So that would be interesting too. Just,
some natural parabolic subgroups.
Right, exactly.
They don't work.
Well, they're too big, right? So
yeah, that's too big. I agree.
That's big, yeah. So they don't help.
Okay.
Yeah.
Thank you.
Okay, more questions? Yes, please.
Yeah, Alberto.
Alberto, I think you muted.
Muted.
Alberto, you should unmute yourself.
About to do that. Okay.
Yeah, good.
Okay, Misha.
Yeah.
Nice to see you. Question. I saw in the description of your talk today something that you may have talked about, but I'm not sure. You were talking about algebras of difference operators.
Right.
I mean, basically one question. If you wanted to replace your difference operators by differential ones,
Mm-hmm.
does all this machinery have something to say about that?
Well, maybe. So in the following sense, it would be something like trying to describe, say, a KP hierarchy, right? KP hierarchy lives on well, pseudo differential operators, but you can still describe it as a single, in a sense, single Plucker relation, right?
Yeah.
It depends on infinitely many parameters. So, well, I don't think it's been done, but it stands to reason that this could be done in this way, right? So you have to embed some into infinite dimensional Grassmannian, but then you also will have to allow additional parameters inside your cluster variable. So I think that way possibly could be done. But difference operators here are present in an obvious way, right? Because we have this when periodic matrices.
Okay. Thank you.
Okay, more questions? Yes.
Yes, I just didn't hear it. So you can construct this generalized structure for any solution of Belavin-Drinfeld.
Well, so if you have data, so let me draw a different example maybe, so that it will be it will be quick, right? So if you have say Kramer-Gervais data, which is well, just root 1 goes into root 2 and root 2 goes to root 3, and you build a similar graph that I've shown before, like this. So this little loop is not considered a cycle. So in this case, the graph that I'm showing is aperiodic, and in this case, you don't need generalized cluster structure. You actually can build the usual cluster structure, and this is done. But if you have a cycle, then you have you necessarily have a generalized cluster structure. But for each data, we know how to construct the corresponding cluster structure. So, well, some of the proofs are in progress, but there is a complete answer for GLN.
For GLN.
Yes. Yeah, and for corresponding double in GLN also there is a corresponding cluster structure.
Okay, any more questions? Okay, so let's thank Michael for the wonderful talk. So thank you, and yeah, there is like this reaction. So thank you very much, and next time we will have Arkady Vainshtein from University of Oregon. So hope to see you all there. So thank you, Michael.
Koля, I'll see you now in my place.
Yes. Soon.
In an hour.
Exactly.
Okay.